Welcome. Um, for a class like this, with students who are coming from a lot of different kinds of background, um, it's a little bit hard to know where to start. And so I'm going to pick a place with starting with the Boltzmann distribution in statistical mechanics, which I'm guessing is familiar to most of you. But if I'm wrong, we can talk about it. Okay, so let me begin with the basic idea here, and then you can tell me if this seems familiar or if it's boring or if it's stuff that you've never heard about. Um, so, um, the idea is that we have uh, a system which is maybe one particle, or it might be many particles, and it has states. Okay, so there's some list of what are the possible states for this particle or many particles. Okay, and maybe we could number them. Hypothetically, states 1, 2, 3, etc. There are probably a lot of states. Maybe there's 10 to the 23rd or vastly more. Okay, but in principle, we could imagine we'll number them. Right? And each of these states has some energy. So same as I can make a list of states, I can make a list of the energies. E1, E2, E3, and so forth. Okay, now suppose that the system is at a fixed temperature, which is some capital T. And at that temperature, the system is in thermal equilibrium. So, this idea of thermal equilibrium is something that you might have seen in classes on thermal physics or in statistical thermodynamics and chemistry. Right? The idea is that the system is exchanging energy with some thermal reservoir. So energy keeps going in, going out, to maintain it in equilibrium at a certain temperature. Okay, and then there is going to be a distribution of probabilities, right? That the system is not necessarily in any one of these states, but it might be in any of the states. And if you keep watching it in time, it'll probably move from one state to another to another. So each of these states has some probability. So there's a probability of being in state 1, P1, P2, P3, etc. Okay, now the idea in the Boltzmann distribution is to say what the probabilities are. Okay. So the idea is that the probability of state number I, okay, so this is P sub I for state I, this is something which is proportional to the exponential of minus the energy of state I divided by Boltzmann's constant times the temperature. Okay, so let me go through what the different symbols are, what these things all mean. Okay, so first,
A
this,
canonical ensemble,
I'm sorry?
right? Are you talking about a canonical ensemble?
Yes. Yes, I am talking about a canonical ensemble. So at fixed temperature. Okay. So here, this symbol, let me mark who maybe this symbol. That means proportional to. I don't know if this symbol has a name. It's the proportional to symbol, which looks kind of like a stretched out alpha, but it's not alpha. It's a proportional to symbol. And that means that the probability P sub I is equal to a constant times the exponential minus E sub I over KT. And so I write that symbol when I don't really care what the constant is. I just want to know that there's some constant there. Okay, but in a minute we can talk about what the constant is. All right, so in this right side of the equation, right, E, this is the 2.71828 dot dot dot, right? This is the base of natural logarithms. E sub I, so I is again the state number. And so E sub I is the energy of state I. Okay, and here T is temperature. So I'm thinking of a system at fixed temperature. So as Cheng said, in the canonical ensemble. And then this K sub B is Boltzmann's constant. Okay, so temperature, I should say, is the absolute temperature. That is the temperature relative to absolute zero, right? So anything that's not at absolute zero is at a positive temperature, right? So this is not the temperature Celsius, where zero is the freezing point of water. It's not the temperature Fahrenheit, where zero is kind of a cold day in Ohio. This is the absolute temperature relative to absolute zero. So on the Kelvin scale, for example. And Boltzmann's constant is K sub B, so that's 1.38 times 10 to the minus 23 joules per Kelvin. So this is basically a conversion factor that converts between energy units and temperature units. Okay, so if you take the absolute temperature and you multiply it by Boltzmann's constant, you get here in the denominator. You have something with units of energy. In the numerator, you also have something with units of energy. So the ratio is energy divided by energy. So it's dimensionless. Right? And the exponential function like sine and cosine and all these other special functions. These things all take a dimensionless input and give you a dimensionless output. Okay, so here I'm putting a dimensionless number into the exponential, and it gives us a dimensionless output to make a probability. Okay, so the idea now is that we have this list of states and a list of energies, and at a fixed temperature, there's a set of probabilities, okay? And so the system has some probability of being in each of those states. This exponential factor tells us what those probabilities are. Okay? And now, whenever you work with probabilities, there's a constraint that the total probabilities have to add up to 1, right? That the system is guaranteed to be in one of the possible states. So we can add up the probabilities and we better get 1 or something is terribly wrong. Okay, that's called normalization. That is, probabilities must add up to 1. So I could write that as the sum over all the states I of the p sub i's has to be equal to 1. Okay. Now, I told you that those p sub i's, those things are a constant times the exponential of minus ei over kt. Right, so that has to equal to 1. That means now if I have this sum, right, of a constant times the exponential, I can factor out the constant, right? It's the same constant for every one of the terms. So it factors out of a sum like this, whoops, exponential minus ei over kt equals 1. And a nice thing about that is that this now tells us what's the constant. Okay, so it tells us we can now divide both sides of the equation by this summation. So we get 1 over the sum of the exponentials. Okay, and now based on this, people say, oh, this denominator is a useful thing, we should give it a name, okay? And so people say that the denominator is, gets the name of the partition function. And people usually give it the letter capital Z. So that is the sum of this exponential minus ei over kt. Okay, now I'm guessing this is the kind of thing that you might have seen in a previous course about thermal physics, or perhaps a chemistry course about introduction to physical chemistry, or thermodynamics and physical chemistry. Am I correct about that? Is this something that is kind of familiar to some of you guys? Yeah. All right. if it's not, you don't have to say so publicly. I mean, you can if you're exceptionally brave, or else you can talk with me separately, and we can talk about what kinds of books would have that kind of background information. Okay? But, you know, and there are ways to derive this Boltzmann distribution, the exponential distribution, based on other more fundamental principles. But I'm just going to start here, okay? All right, so, oh, and one more thing. You know, I'm writing Boltzmann's constant here as K sub B. That's just the way I learned how to write it. People will oftentimes write it as just K with no B subscript. Means the same thing, right? And people will also, especially chemists, will also sometimes, instead of writing K, they write something that they call the ideal gas constant R.
Excuse me, are you writing something?
I'm sorry?
Are
Oh,
you writing?
I am writing, and you're not seeing it. Huh. What happened there?
Maybe this is my problem.
No, it's not
I
your
don't know.
problem.
If
No,
other,
I see it too. It's not. Yeah, it just shows the partition function. As the last thing you
Shows the
wrote was the,
partition function, and it
Yeah.
stopped updating what's on the screen. Well, that's disturbing, isn't it? And I didn't even change anything. It just sort of stopped working. Well, I wonder how I fix it. Okay. I didn't even really change anything on this screen. Huh.
Jonathan,
Yes.
I have a question.
Uh-huh.
Why we blindly tossed on this expression? Because this expression was made only for the ideal gas, where molecules have no any interactions. But in real system, we may have electromagnetic interactions. Sometimes particles may have charge. But then why we are always using this expression?
Okay, so I have both a software question and a physics question here, okay? These are both important. Let me deal with the software question first, and then I'll come to the physics question. Okay, so for the software question, the one thing I know how to do is to turn things off and on again. So I've just turned it off. Now let me turn it on again and see if it works again. I bet it does, right? Do you now see these extra symbols that I wrote?
yeah, I
yes. Yeah, it just updated.
Okay. Well, I guess there's still a few bugs in the system. I wonder why. Okay, the point that I was trying to make as far as nomenclature, and I'm going to come back to Vijay's question in just a second. The point that I was trying to make was people sometimes write this thing with the B subscripts. People sometimes write it with no subscript. People sometimes write also in chemistry this R ideal gas constant, which is K times Avogadro's number. So times 6 times 10 to the 23rd. So it means the same thing. Okay, so that's the point about nomenclature. And I usually write it with the B subscript, but I don't usually say the B subscript. I usually just say K when I'm talking, just to save time. Okay, so that solves the software problem for the moment. That solves the nomenclature problem. Now let's get to the physics problem that Vijaya, am I saying your name correctly?
Yes.
Ultimately, okay, good. So the question was, am I doing something that assumes a non-interacting system? Or what about all the possible interactions? For example, there could be interactions of different charges, right? That would have a Coulomb interaction.
Yes.
And the answer is, I'm not making an approximation yet. I will be making approximations coming up, but not yet, right? So here, all I'm doing is making a list of states, okay? So here, I talk about state number 1, number 2, number 3, and so forth. I have not yet made any assumptions about what the states are, okay? Or what the energies are. And so the energies could well include some kind of interactions between the particles, okay? And so if I say I have two particles and one is at this position and another is at this position, the energy, it might include the kinetic energy of both particles, and it also includes whatever potential energy of interaction there might be. So it might be an electromagnetic interaction or any other kind of interaction. So I am not yet making an approximation about non-interacting particles, okay? So far, this is all just very general that applies to interacting systems as well. But okay, Jack? Okay, great. All right then. Now let's do some examples, right? To go through, how to interpret this sort of formalism. Okay. So let's think about, for example, number 1. Okay, so this would be, suppose we have a single particle with 2 states. So this is what I was writing about in that chapter when I said, suppose a particle could be on the floor or it could be on the table. I don't know why. I was trying to be poetic in that chapter. I'm not sure if it really works, poetry. But let's suppose that it has a low energy state and a high energy state, okay? So I'll write the low energy state way down here, okay? State 1 down there. And then it has a high energy state. State 2, that's up there, okay? So this one has an energy E1, and this one has an energy E2. Okay? And now I know about the probabilities of these states. Okay, so the probability of being in state 1 is this energy, the exponential minus E1 over KT divided by the partition function. That is, it's multiplied by the constant, and the constant is 1 over the partition function. Okay? And the probability for this particle to be in state 2 is the exponential minus E2 over KT divided by the partition function. Okay? So this partition function is the sum of the 2 exponentials. E to the minus E1 over KT plus E to the minus E2 over KT. All right, so this is the world's simplest example of that formalism, right? Where we have just 2 possible states and the probabilities of these 2 states add up to 1. So now for a question, we could ask, which state is more likely? right? Well, that means we want to compare these two probabilities, okay? And so we could say state 1 is more likely than state 2 if the probability 1 is greater than the probability for 2. Okay? So, I mean, that's what more likely means. It's a higher probability. Right? So that means the exponential minus E1 over KT, right, divided by Z is greater than the exponential minus E2 over KT divided by Z. Okay, and now if I want to simplify this expression, well, I can cancel the Z's. That's some positive number, and so I'll multiply through by this positive number in the inequality. Okay, and now I would say, well, I want this exponential minus E1 over KT to be greater than e to the minus E2 over KT. Now I can take the natural log of both sides, right? And so state 1 is more likely if negative E1 over KT is greater than negative E2 over KT. Okay? And now I will multiply through everywhere by negative KT. And because I'm multiplying by a negative number, I have to flip the inequality backwards. Okay? So that means that energy of state 1 has to be less than the energy of state 2. Okay, so this is kind of a simple little point, right? I'm just making the simple little point that the particle is more likely to be in state 1 if the energy of state 1 is low compared to the energy of state 2, right? That at any finite temperature, there's some probability of being in the low energy state, there's some probability of being in the high energy state, but it's more likely to be in the low energy state. So that's maybe not a big surprise, okay? That things tend to be more often in the low energy state. Now, let me do a variation on this example, which is possibly more interesting. So now let's talk about example 2, okay? And so we could say, suppose there is one low energy state so a state like that with energy E1, and suppose there are many high energy states. Okay, so that's many, okay? So these are all different states, and these states all have some energy E2. Okay, so there's a lot of them. Let's say there are n possible high energy states. And this is kind of a common situation, right? It's very common in statistical mechanics that there's one way to have a nice low energy, but there are lots of ways to have high energy. All right, now let's repeat the calculation and see what we can say about probabilities in this situation. So here, for the low energy state, we can say, what's the probability, right? It has to be that the probability is e to the minus e1 over kt divided by z. Okay. Now, what about for the high energy states? Okay, well, there's a probability of e to the minus e2 over kt divided by z to be in this particular state right there. Okay, but what about this one or this one or this one, right? Well, it's all the same, okay? So there's e to the minus e2 over kt over z to be in this state, and the same for this and this and this and this, okay? So again, the sum of the probabilities has to be equal to 1. So that means that the probability of being in the low energy state, so e to the minus e1 over kt divided by z, plus e to the minus e2 over kt divided by z, right? That's for the first one. And then for the next one, e to the minus e2 over kt divided by z, plus the same thing for the third one, the fourth one, the fifth one, etc. Right? All those things have to add up to 1. Okay? And of course, there are n such states where n might be a really big number. Okay? So continuing that on, okay, that means that e to the minus e1 over kt divided by z plus n times e to the minus e2 over kt divided by z has to be 1. Well, one thing that we can get from this is just what's the partition function now, right? Because if we multiply through by z, we get that e to the minus e1 over kt plus n times e to the minus e2 over kt equals z. So this is the partition function, right, in this example. But let me ask something that's maybe simpler and more important, okay? And we could say, let's go back to the question of which state is more likely. Right? Is it more likely to be in the one low energy state, or is it more likely to be in one of the many high energy states? Okay. That is to say, for the second of these options, right? I don't care which of the high energy states it's in, right? But what's the chance that it's in one of those many, many high energy states? If we want to figure that out, we want to compare what's the probability, right, down there versus the sum, this probability plus this one, plus this, plus this, plus this, right? Any of these possibilities. So let's do the comparison. So we'll say the low energy state is more likely if the probability of being there in P1 is greater than the sum of being in any of the high energy states, right? So that is the sum of P2 plus P3 plus P4, right? Plus all the possibilities up there. So that means we need e to the minus e1 over kt, right, divided by this partition function, has to be greater than the sum of all those possibilities. And there are n such things. So that's a factor of n times e to the minus e2 over kt divided by z. Okay, now let's simplify this expression the same way that we were doing before. Okay? So we can multiply through by a factor of z, right, just to cancel those factors of z. So we have e to the minus e1 over kt has to be greater than n times e to the minus e2 over kt. Okay. Now, let's take the natural log of both sides of this equation, or this inequality. Okay, so that means that I need this negative e1 over kt has to be greater than the natural log of n times this exponential. Okay, so incidentally, when I write log, L-O-G, I mean natural log, always. I never mean log base 10. All right, and so if you know how to simplify an expression with a log, right, you know that the log of a product is the sum of the logs, okay? So this is the log of n plus the log, whoops, what did I do? Plus the log of the exponential e to the minus e2 over kt. And the log of an exponential is just the thing that you start with, right? Because the log is the inverse function of the exponential, right? And so this is equal to negative e2 over kt plus log n. Okay, so now I will multiply both sides of this inequality by negative kt. So that means that I need to flip the inequality once again. Okay, so that means I need E1 to be less than E2 minus KT log N. Okay, now let's think about this result. Whoops, and this is an E sub 2, excuse me. Let's think about this result, right? So here, we're comparing the energy of the low energy state, right? We're comparing this E1 with something. But the something that we're comparing with is not just E2. The something is a modified version of E2, right? It's E2 with this correction term, right? There's the E2, and here is some kind of correction term that's making a modification of E2 to take into account the multiplicity, the fact that there are many of those high energy states. Okay. So this corrected energy gets a special name, okay? This corrected energy is called the free energy. Okay, so to write that out, okay, we could say the free energy of the family of high energy states, okay, of the high energy state ensemble, this high energy state collection, right? A set of many such states, right? That is some F2 is E2, the energy, minus this correction term, KT log N, the number of states in this family. And maybe just to make it look nice, I'll write N sub 2, because it's the number of states in the high energy state family. In the family, or the collection, whatever we want to call it, the group of states.
Excuse me.
Please.
Did you mean grouping all the high energy states together reduces the energy of the high energy states, the energy of the high energy state effectively?
If, as far as this comparison goes, right? So the states in this collection, family, whatever we want to call it, they still have an energy, E2, but they have a free energy, F2, which is lower, right? It's reduced compared to the energy by this extra logarithmic term, okay? And now I keep trying to make up silly little names for this thing. So instead of calling this a family or a collection, the word that people really use for this sort of thing is a macro state. in the so I won't call it a state collection or family, but the serious word, if you want to sound like you know what you're talking about, is a macrostate, right? That is a grouping of many microstates, okay, the individual states. And now there is a word for the thing that is getting subtracted off, okay? So let's look at everything that's getting subtracted off, except for the temperature thing. Okay, so if we look at what is getting subtracted off, that gets a special name. This is called the entropy of the macrostate. Which is written with the symbol S2, which is Boltzmann's constant times the log of the number of microstates in the macrostate. Right? N2 is number of microstates in the macrostate. That is, how many microstates are getting grouped together? Question?
You didn't really talk about it in the chapter, but do you lose any precision in measuring or manipulating these states when you group them together as a macro state, or does it just make the math easier?
Well, I'm losing any information about which of these microstates the thing is in, right? And so in the chapter I was talking about, different tables, right? And so I'm grouping them together, and I'm saying, what's the probability of being on any one of the tables? And I don't care which one, right? And so I'm, yes, I am losing that kind of information. Mm-hmm.
Okay.
And now I was using this terminology of free energy to refer to the high energy place, but we could do the same thing for the low energy. We could say, what is the free energy of macro state number one, the low energy one, okay? Well, in this case, there's only one microstate that goes into that macro state, right? Back in this picture here.
I'm sorry, are you writing right now?
Oh, all right. There's a bug in here. I've got to get this fixed. I'll find some other way to do this. All right, I just quickly turn it off and on, and then I'm sure it's going to work again. Here, I'm back to this picture, and you can see it again, right? Okay. All right, there's only one microstate in this macrostate. Okay, so if I go down here, I will say, all right, there's only one microstate. That means there's one microstate in macrostate one. So N1 is 1. So the entropy that is KT times the log of 1. But the log of 1 is 0. So that's 0. Okay. So the free energy of macrostate 1, that's the energy of macrostate 1 minus T times the entropy of macrostate 1, which is 0, right? So this is just the energy of macrostate 1, okay? So there's no correction that's needed, right? In this case, where there's only a single microstate, goes into that macrostate, there's no need for any correction, okay? But in the high energy place, we would say that there is a big multiplicity, and so you have many possible microstates, and so that does make a big correction. Okay, so from this we get that macrostate 1 is more likely than macrostate 2 if F1 is less than F2. Okay, that is comparing the free energies. Okay. I'm going to keep talking for just a few more minutes to finish this story. If any of you have to go, you can come back and see the recording later. Okay, all right. That's fine. If you have to go, you can go. Okay, so finishing this story then, this is showing you something about free energy. And it's showing you that free energy, is an appropriate thing to compare when you're comparing these different macrostates. Okay. Now, there's a possible objection that some of you might be thinking, right? So some of you who have had statistical mechanics courses might be thinking to yourselves, wait a minute, I have seen a definition of free energy and it's not that, right? Some of you might be thinking that you have seen free energy is not the free energy of a state, there is just the free energy for a stat mech system, okay? So if you look for the free energy, okay, some of you might have seen a definition that it is equal to negative kT times the log of the partition function, right? Is this a definition that's maybe familiar to some of you? I'm not seeing a whole lot of reactions. So maybe yes, maybe no.
Yes.
If you know what I'm saying, that's great. If you don't know, then don't worry about it. So you might be saying, wait a minute, this definition doesn't look like it has anything to do with the definition that I was just trying to illustrate to you with my cute little examples. Okay. So actually there is a relationship. Okay. To see the relationship, let's play around with this definition for a minute, okay? So here we could divide both sides and say by negative kT, right? And then take the exponential of both sides. So exponential minus f over kT is the exponential of the log of z, which is just z. Right? So that means the sum over of this factor, e to the minus energy over kT for state 1 plus state 2 plus state 3, and all of those things, added together. Right? So that means in my example 2, that means e to the minus e1 over kt plus n2 times e to the minus e2 over kt, right? This thing is the partition function for the state, the system with one low energy state and many high energy states. Okay. So what I am doing here is grouping together all the things that are getting added up in the partition function, right? So I am saying, let's look at this combination as e to the minus f2 over kt. And let's look at this combination as e to the minus f1 over kt, right? And so when I group together a bunch of microstates as a macrostate, that means I'm grouping together a bunch of terms in the partition function and associating a single free energy with that group of terms. And the same thing over here, but now there's only one term in that group. So this is what goes by the name of coarse graining, right? It's zooming out. It's not looking at all the fine details of a system, but just looking at what we decide is important, right? And what we decide is important in this case is the thing in a low energy or is it in a high energy? Okay, so that has to do with the relationship between the thing that I was showing you and the free energy that you might have learned about in statistical mechanics classes. Okay. So let me wrap up by giving what may be some of the lessons of this story. Okay. So the general lessons that I want to take away from here and apply to other problems. Right? Lesson number 1 is the idea of coarse graining. Right? That is that we group microstates into macrostates. Okay. Lesson 2 is the idea of the free energy. Okay, so that is we have a correction to the energy. We have the energy minus temperature times entropy. And that shows you the combination of energy and multiplicity, right? That entropy has this information about multiplicity of a macrostate. And both of those things are important when we want to think about what's more likely, right? And then third, that there's an importance of temperature. That temperature goes into the free energy. And if you're at low temperature, the energy is more important. If you are at a high temperature, the entropy or the multiplicity of the states is more important. And this temperature factor in the free energy is giving you a specific way to see what's more important, at low temperature or at high temperature. All right, so that's my story about this. I'm sorry I went a little bit over time. Sorry about that. Okay, so are there questions about this in general, or would you guys maybe like to wait until you see specific examples of how to work with this?
Wait until you see examples.
More examples. Okay. So yeah, this is all very general, but I'm going to get into examples starting in the next class on Wednesday. And so I am starting with an example about magnetism. So please take a look at the first section of chapter 2, and I'm going to start talking about that on Wednesday, and we can see how some of these things work in practice. Okay, I'll stop talking for now, and if anybody wants to stick around to talk about questions, that's fine. Otherwise, the rest of you can go. All right, thanks, you guys. I'll see you on Wednesday.